Chapter 13, Universal Gravitation. Newton's law of universal gravitation states that every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. For example, if we have two particles of mass m1 and m2, and with a separation of r, mass m1 will attract mass m2 by a force, we name it F12. That is a force 1 to the 2. According to Newton's third law, when one particle exerts a force on the other, as a reaction, the other particle will exert a same magnitude but opposite direction force. We name it F21. Now, in this case, F12, the magnitude equals to of F21 because that is a pair of action-reaction forces. However, the nature of this pair of attractive forces is gravitational force. According to Newton's law of universal gravitation, it follows this formula that is proportional to the product of their masses and inversely proportional to the distance squared. And when we say proportional, then we can place a constant. In this case, we use a capital G. It has a special meaning. I will explain that later. Then we will make that equation. Now, first of all, let's discuss about mass. Well, in SI unit, mass is in kilogram. In this case, as a matter of fact, the mass is gravitational attraction mass. It is different compared to the inertia mass that we learned from Newton's second law. However, when we use SI unit in kilogram, somehow the particle's gravitational mass equals to its inertia. So we can safely use its inertia mass for the calculation. Secondly, the inverse square law, it is a very interesting situation. It will give us a consequence that the gravitational force exerted on a finite-sized spherical symmetric mass distribution. For example, let's talk about Earth. Earth is very close to a spherical distribution of mass. Now, the gravitational force exerted by a finite-sized spherical symmetric mass distribution on a particle outside the distribution is the same as if the entire mass of the distribution were concentrated at the center. So, in the future, when we have a spherical distribution, we can safely, if mass is uniformly distributed, we can safely assume that the mass of this spherical distribution as if concentrated at the center. So, mass of the Earth we can mark at the center. Therefore, if the particle of mass little m has a distance of h, which in this case we call this altitude, above the surface of the Earth, and the distance from the center of the Earth to that particle, obviously that little r equals to radius of the Earth, which is this part, plus altitude h. That is the separation between mass of the Earth and that particle of mass little m. We're going to have a chance to prove this theory. This is called Newton's shell theory when you learn physics 1c. Now, another interesting constant here is a so-called universal gravitation constant, capital G. Measuring this G requires relatively accurate and sophisticated equipment. Well, that was actually done in the year of 1700 in the lab of called Cavendish Laboratory. And the result is quite astonishing. That capital G in SI unit equals to 6.67 times 10 to the negative 11 of so-called SI unit. This capital G must carry units to balance the left and the right side of the equation. Let's take a look. If the left side of the equation is in Newton, well, Newton actually is kilogram times meter per second squared. Well, on the right side, we have mass times mass, which is kilogram squared, and this is in meter squared. So the G has to choose the SI units that balance the left and the right. Now, how do we calculate the gravitational force between a point mass and an extended body? For example, this is a one-dimensional ruler of mass, let's give it capital M, of length capital L. Let's establish a x coordinate, which is one-dimensional. This is x equals 0, and obviously this will be x equals to L. Assume that we have a point mass located a distance little b away from the far end of this ruler. Now, what is the gravitational attraction between the ruler and this point mass M? Well, some of you might think, well, since this is a uniform distributed ruler, the center of mass should be here. Can we just assume the total mass, capital M, located right here, and then we directly apply the Newton's law of universal gravitation that we just learned, which is Fg equals to the capital G times M1, M2 divided by their separation square. In this case, it looks like it's half of the length of the ruler plus b. Well, I'm going to prove it. That cannot be done because we just learned only when we have a spherical symmetric mass distribution that we can assume that its entire mass of distribution were concentrated at the center. This is a one-dimensional ruler. It's not a spherical symmetric mass distribution. Therefore, we cannot assume the gravitational mass concentrated at its center and directly apply the Newton's law of universal gravitation. What we need to do is we have to cut a very small piece, name it dm. Since it's so small, that is as a point mass. So let's calculate what is the gravitational attraction between this point mass dm and that m. Well, since both are points, so we can directly apply this equation, which is Fg, gravitational force between these two point masses. Let's say that is the dm attracts on this little m, okay, that is called df. So let's name this dfg equals to a capital G and 2 point masses. One is the point mass m itself, the other is the slice we cut. We name it dm, very small, so this as if m1, m2 divided by their separation square. And right now the separation should be between dm and this little m. So it should be L plus B minus X. Inverse law square, don't forget about scale. Why is that? Because that the length of ruler is L plus B and give you this much. Where do we cut this dm? We cut this dm x meters away from the origin of the x-axis. Therefore, L plus B minus X give us the separation between dm and this mass m. Okay, so we established the force between this dm and this m. How many pieces of dm that we have? As you can see, many pieces. So we have to add all of them. Now be very careful, this dfg is a vector. However, you can imagine if we cut another piece and look at the blue one. If this is called dm of prime, well, if that point mass exerted force on this m, let's call dfg of prime. Well, because this is always attractive force, so the dFg prime has the same direction as dFg. So these two forces can be added directly because they have the same direction. Therefore, we can safely add all the dFg because they have the same direction. Therefore, that we expect the total gravitational force between the ruler and point mass m is the summation of all the little dFg. That gives us this result. Now what do we do? Since our ruler, this extended body, starts from x equals 0 and at x equal to L, so we say 0 to L. Now, we need to finish this integral. This is a mass procedure. So what we do is, well, assume that the ruler has a uniform mass. One-dimensional density, we usually use that little mu, that equals to total mass of the ruler divided by total length of the ruler. Since it's uniform, the size we cut is dx. So therefore, dm should equals to the density times its size called dx. Now, we are going to plug in this dm expression into our formula. This integral is from 0 to L and capital G m. Our dm is replaced by mu d of x and L plus b minus x of square. Now what do we do next? Well, let's take a look. Constant, constant, constant. So we don't have to worry about it. Well, as far as for the dx, we can add a little negative sign inside and we time a little negative sign outside. We still balance the equation. Okay. On the other hand, look at this. L plus b is a constant. So as a matter of fact, we learned from calculus that d of L plus b minus x actually comes out as d of negative x. Why is that? Because when you differentiate a constant, that will be 0, then plus you differentiate the negative x, which is this term. This is what's left. So this indicates that the d negative x can be replaced by d of L plus b minus x. So, as you can see, that we have a negative sign and constant g m mu. We can pull this out of the sign of integral, and this d negative x can be replaced by d of L plus b minus x. And we still have that denominator. Well, this time I think you feel more comfortable because you see a pattern of d of something over that something of square. So if I change this pattern a little bit more, I think you will feel even more comfortable. That is, I'm going to get this L plus b minus x at denominator as the numerator. Have this negative 2 in front of it and d of L plus b minus x. Okay? So, as you can tell, we're going to be able to finish this. Here we go. Now, the result of total gravitational force between the ruler and the point mass should equals to this negative g m of u. Okay. Now, according to the rule integral, that what we come out is negative 2 plus 1 as a coefficient. And then L plus b minus x of negative 2 plus 1 from x equals to 0 to x equals to L. Okay. So, you can see this is negative 1, negative cancels. Capital G, little m. This mu is linear density replaced by the mass of the ruler divided by length of the ruler. And this actually is 1 over that L plus b minus x. So therefore, if we plug in, what we have is from x equal to L. So this is L plus B. If we plug in x equal to L, that's minus L. Minus of L plus B when x equal to 0. Minus 0 is the result. So L and negative cancels, and the result that we have is G M M. Here is a L, and this is 1 over B, and that is 1 over L plus B. Let's take a look at this. First of all, I think the units are right, because gravitational force suppose equal to capital G times the production of two masses divided by the distance squared. So since this is the distance, and this combination also means another distance, so the units is right. However, imagine from the very beginning, if we assume the mass of the ruler is right here as capital M, and this is half L, a point mass of mass little m is little b away from the far end of the ruler. If we directly apply Newton's law of universal gravitation, assuming between this point mass and that point mass, what we have is F of G equals to capital G of capital M, little m, over, what is the distance? Little b plus half L. So it is little b plus half L, that distance square. Now obviously, this is completely different compared to that one. So therefore, from the very beginning that I explained, only when your distribution is a spherical symmetric object that you can assume its gravitational mass is at its center. Otherwise you cannot. So the ruler is not a spherical symmetric object. So we cannot assume the gravitational mass concentrated at center. We must cut a small slice and name it dm, and we must calculate the gravitational attraction between this point mass dm and that particle m to find the dfg. Then we add all the dfg and we get our correct result, which is this one. Okay, gravitational force caused object to fall, that we learned from our previous chapters, which is especially from Physics 1A. Now, let's talk about the dynamic of this case. First of all, this is Earth. Since Earth is a spherical symmetric, pretty close to spherical symmetric mass distribution, so we can assume mass of the Earth is concentrated at its center, and this is radius of Earth, RE. If we have a point mass, a little m, h meters above the surface of the Earth, this h actually is altitude. So the separation now between the little m and me, which is mass of the Earth, is re plus h. So assume Earth exert a gravitational attraction on little m. Well, certainly, as a reaction, the little m also exert a force on the center of the Earth, on the mass of the Earth. It's same magnitude, opposite direction. Well, since they have the same magnitude, a force on the little mass will cause very large acceleration. The same amount of force on the large mass of the Earth will cause very small acceleration. Therefore, what we see is that the object falls towards the Earth. We do not see the Earth jumps up because the little m attracts the Earth. Okay, this Fg can be expressed as, since this is a point, assuming this is concentrated center, so it's point mass, capital G, little m, mass of the Earth, divided by their separation square. Separation is Re plus h. Don't forget about this square. Okay. Now we learned that if there's a force on the object, if we ignore the air friction, and when this object falls, that's called so-called free falling, then it will cause an acceleration. So this is a force on the little m, so little m is going to have an acceleration. This acceleration is so special because it's caused by gravitational force. We give a special symbol of little g. This little g stands for gravitational acceleration constant. So if we want to get this value of little g, as you can see, that when mass m cancels, this little g equals to capital G. When the mass cancels, you have this mass of the Earth left and radius of the Earth plus altitude of square. Now, radius of the Earth is very close to 4,000 miles, or we say 6,400 of kilometers. Well, actually, the Earth is a little bit elongated. It has relatively larger radius at the equator compared to the radius to the North or South Pole, because 5 billion years ago, when we have a supernova that established our solar system, Earth is relatively hot and soft, but still spinning. Spinning will cause a jello elongated around its orbital region. Therefore, the radius around the equator is a little bit larger compared to the radius to the North or South Pole. Okay. Now, since radius of the Earth is around 6,400 kilometers, if we consider an object near the surface of the Earth, say for example, if you go to the top of Mount Everest, h probably is around 8.4 kilometers. 8.4 kilometers compared to 6,400 kilometers, this is a very small add-on. So when that happens, as long as anything is under the top of Mount Everest, we can ignore this little h and we give this g me over re squared. If we plug in the right number for capital G, which is 6.67 times 10 to negative 11 of SI unit, mass of the Earth is around 5.9 times 10 to the 24 kilogram. And we plug in this in SI unit, which is meter, should be around 6.4 times 10 to the 6 of meter. And it comes out very close to 9.8 of meter per second squared. This is a very useful constant that you will use many times in this chapter. But this is a so-called gravitational acceleration constant near the surface of the Earth. If we consider the gravitational acceleration constant near other terrestrial planets, for example, if we calculate G on the Mars, then we have to plug in the mass of the Mars here and the radius of Mars here. And after the calculation, we will get the G near the surface of Mars. And I mentioned that only when h, the altitude, is relatively small compared to the radius of the Earth, and you can ignore this little h. Otherwise, that you have to take that h into consideration. For example, if we talk about variation of g with altitude h, on your textbook, page 395, there is a table. It gives us a list of very interesting results that tells us that when the h goes very large, and the little g will decrease dramatically. For example, when altitude h is 1,000 kilometers, the g will come out as 7.33 meter per second squared. And if we reach 2,000 kilometers, which means we doubled altitude, that g will drop to 5.68 of meter per second squared. So let's see. When h is 1,000 kilometers, the g is already smaller than 9.8 meter per second square. It is 7.33 of meter per second square. And when h is 2,000 of kilometer, well, pay attention, we're not going to get half of that, okay? And the result is 5.68 of meter per second square. So little g varies according to its altitude. And one more thing I want to mention is that the G around the equatorial region is slightly smaller than the G at the North Pole, South Pole, because look at this equation. If we're near the surface of the Earth, we can ignore H. But when you plug in radius of the Earth around the equator, this RE is relatively bigger compared to the radius of the Earth of North Pole or South Pole. So the G at North Pole, South Pole will relatively bigger compared to the G at equator. So for example, the country as Sweden, which is pretty close to the North Pole, and the G value is around 9.83 of meter per second squared. But the country near the equator probably will have a G of 9.73 meter per second squared. That is the variation due to the latitude we call.